So far, much of what we've seen in geometry has been a little bit abstract, and maybe things have even seemed a little bit weird. We have proved that the sum of the measures of the interior angles on a triangle are always less than or equal to 180 degrees, but we've been used to, in previous courses, working with the interior angles always exactly equaling 180 degrees in measure. Similarly, we've had our Sakari quadrilaterals, which look like they should be rectangles based on our familiar geometry, but aren't necessarily. At least we haven't been able to prove it. And so much of what we've done has gotten sort of up to a point we're familiar with, but we've reached sort of a barrier. We haven't been able to push past to get to some of the things that we're most familiar with. And our experience here is not at all unlike the experience that mathematicians worked on historically when going through geometry and running into these barriers and trying to rigorously prove the results that experimentation and intuition even suggested should be the case. One of the first people to rigorously attempt to put geometry on a firm foundation was Euclid, who lived in ancient Greece in a few centuries before the birth of Christ. And he had a number of postulates that he worked with that are similar to the axioms that we've been working on. And he had 5 of them, 5 most basic ones that he looked at to begin with. And the 5th postulate was what we call now the parallel postulate. And unlike the first 4 postulates, which were very, very simple, things like given any 2 points, there's exactly 1 line between them. It's a very simple statement, very intuitive. Or given a point and a radius, there's always a circle with that center and that radius. Also, very simple. Those are a couple of the postulates that he worked with. But then he got to the point where he wanted to prove things about rectangles and triangles, and he needed something else. And his 5th postulate, which we call the parallel postulate, was the following. So we're calling this one axiom P1, or we'll also often call it the parallel postulate. And the axiom says, given a line L and a point P not on L, there is a unique line L prime such that P belongs to L prime and L is parallel to L prime. So the sketch of what's going on here, we've got some line L, we've got a point P, and what this axiom is saying is that there is exactly 1 line that passes through P and is parallel to the original line L. This matches with our intuition. This matches our experience in real life, but it's also a little bit cumbersome. This is a more complex statement, a more complex figure than the other postulates that Euclid worked with. It's even more complicated than many of the axioms we've looked at. Euclid himself wasn't super satisfied with it. He waited a long time. He avoided using this axiom as long as possible in his treatment of geometry, and only went back to it when absolutely necessary. It was believed for a long time in the mathematical community that followed Euclid's tradition that this postulate didn't need to be a postulate, that it should be possible to prove this. prove this statement, that there's only one line parallel to L passing through P. We definitely know there is one. We've seen that already. We can use our constructions, particularly with respect to perpendicular lines, in order to show that there is at least one parallel line through P. But proving that there isn't another one eluded mathematicians for a long time. And in fact, for thousands of years, mathematicians attempted to prove the fifth postulate, Euclid's fifth postulate, using the others. And proofs were published, and errors were found, and proofs were published, and errors were found. And then finally, in the 19th century, a few Russian mathematicians finally dared to imagine the possibility that maybe the parallel postulate isn't provable using the other ones. Maybe it actually can't be used as a theorem. In other words, maybe there exist geometries where this statement is not true. And they proved it. They constructed geometries that satisfy all the other axioms of geometry, but not this one. They constructed geometries where any 2 points have a single line through them, etc., etc., but you have more than one parallel line passing through a given point. And this broke the field of geometry wide open. All of a sudden, we've got all of these fairly exotic geometries to look at and study. And at that point, we really saw the distinguishing between Euclidean geometry and non-Euclidean geometry. Euclidean geometry is geometry in which the parallel postulate holds. So let's specify, let's state that here. A geometry is called Euclidean if axiom P1 holds. If there's only one parallel line through a given point. It's called non-Euclidean otherwise. So what we're going to do now for the next few weeks is study Euclidean geometry. We're going to study geometries where the parallel postulate holds. After a few weeks, we're going to come back and we're going to examine the alternative possibility, examine the possibility that parallel lines are not unique. And all the stuff that we do from now until then won't apply under that new regime. So, until further notice, all geometries will be Euclidean. They will satisfy the parallel postulate, and this is going to mean that we're working in the type of geometry that we have seen a lot in previous courses. All right, so the parallel postulate, it turns out, gives us a huge amount. There's a whole bunch that we can do with the parallel postulate. So what we're going to do right now is we're going to look at a bunch of theorems, most of which are strengthened versions of theorems that we already had. Before, where a theorem might have had a less than or equal to, now we're going to have an equality. Before, where maybe it was just a there exists such a thing, now we'll be able to say there exists a unique thing, as in the axiom here. So let's look at our first theorem. And this theorem is going to be extremely helpful. We're going to keep making reference to it over and over again. So theorem 76. If M, the line M, is a transversal to L and L prime, the following are equivalent. there's going to be 5 statements here, and all 5 of them are equivalent to the others, meaning if you know any one of these statements about M, L, and L prime, then you know all of the others. So the first statement is that L is parallel to L prime. The second is that some pair of alternate interior angles are congruent. Number 3, some pair of corresponding angles are congruent. Number 4, all pairs of alternate interior angles are congruent. And number 5, all pairs of corresponding angles are congruent. Let's just make sure and remind ourselves of how the setup goes here. So in a transversal, all 3 lines are coplanar, so everything lies on the same plane. And M intersects the lines L and L prime in 2 distinct points. And so we have the following. We have alternate interior angles. There and there, for instance, there are 2 pairs of alternate interior angles. And then we have corresponding angles, and then we've got a bunch of pairs of those. An example would be the 2 red angles are corresponding. And we know some of this theorem already. Some parts of this theorem are fairly obvious, whereas others are going to depend on the parallel postulate that we just had. And we are not going to make direct reference to the parallel postulate super often, actually. Most of the time, when we are going to prove something that requires us to be working in Euclidean geometry, we're going to really be using Theorem 76. Theorem 76 is, in some ways, the most useful form of the parallel postulate that we're going to be working with. All right, so let's see a proof of this. Now, when working with the following are equivalent type statements, you want to show that each one of these statements implies each of the other ones. Now, you don't do this, you don't do all of those implications. You don't show that 1 implies 2 and 3 and 4 and 5, and then prove that 2 implies 1 and 3 and 4 and 5. What you do is you construct a sort of network of implications, and you show that if you know one of the statements, you can say that, oh, if I've got this statement, then that means this other statement, and then I've proved that that one implies the third one, that one implies the fourth one, and you prove that you can get from any one of your statements to any other one of your statements by following a chain of implications that you've proved. A lot of times, you prove this by proving simply that 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, 5 implies 1. Go through it linearly like that. However, certain problems, such as this one, don't lend themselves to that, and we're going to sort of make a more complex web of implications here. So let's see what we've got. Now, we already know some implications here. Theorem 69 gives us the implications 2 implies 1 and 3 implies 1. We already knew, actually, that if the alternate interior angles are congruent, then the lines L and L prime are parallel, and similarly for the corresponding angles. We already knew that, and we did that by the exterior angle theorem. So that gives us some things. Implications 4 implies 2 and 5 implies 3 are obvious. So 4 says all pairs of alternate interior angles are congruent. 2 says just that some pair of alternate interior angles are congruent. So clearly, if all of them are congruent, then any pair is going to be congruent. So 4 implies 2, 5 implies 3 are totally obvious. Now, the implications 2 implies 4, and 5 implies 3 are obtained by using linear pairs and vertical angles. Now, this is not actually a proof here. This should be seen as sort of a proof sketch sort of thing. But to talk about what I mean here, let's suppose that we know that the 2 blue angles are congruent. Let's say that we know that some pair of alternate interior angles are congruent. Let's say we know the blue ones are congruent. Then since the 2 green angles form linear pairs with the 2 blue angles, and the 2 blue angles are congruent, that shows us that the 2 green angles are congruent. So that shows us that if some pair of interior angles are congruent, then all of the pairs of interior angles are congruent. Similarly, we can do the corresponding angles here. If we have the 2 corresponding angles that I had before are congruent to each other, and then we want to look at the 2 now yellow corresponding angles, then if the red angles are congruent, then since the yellow angles are vertical to the red angles, they are also congruent to each other. And you can get the other corresponding angles using a linear pair argument, similarly to how we did the alternate interior angles. So that gives us implications 2 to 4 and 5 to 3. So let's look at the chain of implications that we have so far. And I'm going to use a little diagram here to keep track of where we're at. All right, so we have 2 implies 1, we have 3 implies 1, we have 4 implies 2, and 2 implies 4, and we have 3 implies 5, and 5 implies 3. That's what we've gotten so far. Now we need to start filling this up. So next, let's go ahead and prove that 5 implies 4. Now, if all pairs of corresponding angles are congruent, then all pairs of alternate interior angles are congruent. Since if we take the vertical angle of one of our alternate interior angles, we get a corresponding angle pair. Let me explain that. So let's suppose that we know that all pairs of corresponding angles are congruent to each other. And let's look at a couple of alternate interior angles. So we want to know that the alternate interior angles, the blue and green alternate interior angles, are congruent to one another. assuming that all the pairs of corresponding angles are congruent to one another. Well, the blue angle is congruent to the other blue angle because they form a vertical pair. So the two blue angles are congruent, and furthermore, the upper blue angle is congruent to the green angle because we've assumed that all pairs of corresponding angles are congruent, and those are two corresponding angles. Therefore, the green angle is congruent to the upper blue angle, which is congruent to the lower blue angle. So the two alternate interior angles are congruent. So this shows that 0.5 here implies 4. All right, so we've got a web of implications now, and the one that's left that we're going to prove using the parallel postulate, which you notice we haven't used yet, is 1 to 5. Now, before we go and prove 1 implies, not 1 implies 5, but 1 implies 3. Sorry about that. We're going to prove 1 implies 3. Now, once we have that 1 implies 3, that's actually going to show that all of the statements in this theorem are equivalent to one another. Because once we have that 1 implies 3, we can get from any point on the on this diagram to any other point. So, for instance, if we wanted to show that 2 implies 5, once we have the line from 1 to 3, we know that 2 implies 1, and then 1 implies 3, and then 3 implies 5. And similarly, we can connect up the any two of these points. Any one of these statements implies any of the other statements. So it remains to prove 1 implies 3. That is to prove that some pair of corresponding angles are congruent, given that the two lines are parallel. And this is where we are going to use the parallel postulate. All right, so here we go. All right, so now let's prove that 1 implies 3. So let's suppose that L is parallel to L prime. We're going to show that that some pair of corresponding angles are congruent. Now, we are going to need to make reference to a bunch of the angles in the problem, so I need to give them names. Let me go ahead and sketch out my diagram first, and go from there. And I want to make sure that that I get all my names correct. All right, there we go. Actually, I'm going to expand a little bit on this from where the notes have it. All right, so let's do that. Let's let P be in L prime intersect M, Q be in L intersect M, R be such that QPR, A in L and B in L prime such that A and B are on the same side of M. All right, we've supposed that L is parallel to L prime. All right, so now we're going to compare, we're going to look at this angle here and compare the angle AQP. We're going to compare it to the angle BPR. So now, by angle construction, there is a ray PC with C on the B side of M with the angle RPC congruent to the angle PQA. So by angle construction, there's some ray out here that does this. With this angle like that. So now, by Theorem 69, we have that the line PC is parallel to the line L, since the angle PQA and the angle RPC are corresponding and congruent angles. So we've got that PC and, pardon me, we have that the line PC and the line L are parallel, but they both include the point P. So by axiom P1, by the parallel postulate, there is only one line through P and parallel to L. So that means that the line PC must equal the line L prime, because they are both lines through P that are parallel to L. Therefore, C is in L prime, and we also know that it's on the B side of M. And so this means that the ray PC is equal to the ray PB. Thus, this means that the angle RPB is congruent to the is equal, really, to the angle RPC, which is congruent to the angle PQA. And that does it for us. That shows us that a pair of corresponding angles between L and L prime are congruent, which finishes up that chain of implications that we had before. So we're going to use this a lot. A lot of what we're going to do is going to involve taking parallel lines L and L prime and M, transversal, and knowing that the corresponding angles are congruent, that the alternate interior angles are congruent, and so forth. Let's see a quick application of that right away. So Theorem 77 says that given triangle ABC, the measure of angle A plus the measure of angle B plus the measure of angle C is equal to 180. We had another theorem that told us that the sum of the interior angles is less than or equal to 180, but now we have that they're actually equal. So the proof, I'm just going to sketch this out, and the diagram, or I'll get it started, but then the diagram will carry the day. So let's give ourselves a triangle A, B, and C. So one of the things that we are going to wind up doing a lot is taking parallel lines that pass through a certain point. And because of the parallel postulate, we know that there's only one of them. So we can say something like the following. Let's let L be the line through B and parallel to the line AC. Given this, we now can think of the two lines L and the line AC. Now that they're parallel, we know that all transversals give us a whole bunch of congruent angles. In particular, the line AB is a transversal to the lines AC and L. And so, if we look at this pair of alternate interior angles, the red ones, they have to be congruent to one another. We didn't know that before the parallel postulate. Similarly, we know that the two green angles have to be congruent because the line L is parallel to the line AC. And this is what's going to give it to us. So let L be the line through B and parallel to AC. And let's let D and E be in L such that, let's see, what do we want? We want DBC, DBE rather. And let's see, D is on the A side of the line BC. Just making sure that we have our points specified properly. Excuse me. So now, by Theorem 76 rather, the angle A is congruent to the angle ABD, and the angle C is congruent to the angle CBE. So now the idea is that we have the three angles, the red, the blue, and the green, and you'll notice they sort of form a linear triple rather than a linear pair, but the point is that they're all going to add up to a measure of 180. Let's be really precise about this. So what we need to do is use angle addition in order to get to exactly where we want. So we want to know that, let's see, we want to know that the point A is in the interior of the angle DBC. We have that A is on the D side of BC. We chose that when we specified what D was. And we want to know that A is on the C side of BD. Since the line AC is parallel to the line BD, we have that A is on the C side of the line BD. So this tells us that A is in the interior of angle DBC. So this means that the measure of angle DBC is equal to the measure of angle DBA plus the measure of angle ABC. But then we also have that the measure of angle DBC plus the measure of angle CBE is equal to 180. So putting all these things together, let me see if I can give myself just one more line here rather than having to go to a new slide. So we have that the measure of angle A plus the measure of angle. I don't want to write the measure of angle B again because there's more than one angle at B we can talk about. So that's the measure of angle ABC plus the measure of angle C is equal to, we already showed that angle A is congruent to the angle ABD. So that's the measure of angle ABD plus the measure of angle ABC plus the measure of angle, angle C is congruent to angle CBE. On the previous line, we showed that, or the second to last line before, showed that the measure of angle DBC is the measure of angle DBA plus ABC. So this is going to give us the measure of angle DBC plus the measure of angle CBE. So that's just looking at this angle here. And then the measure of angle DBC plus the measure of angle CBE is 180 because they form a linear pair, as we mentioned just before. So that finishes it off. And so that's how we can use the parallel postulate to prove that the interior angles of a triangle really do add up to 180 in measure. Okay, so we've got this, and actually once we have this, then the Euclidean version of the exterior angle theorem becomes really easy. So Theorem 78, which we'll call the Euclidean exterior angle theorem, it says, given the exterior angle to a triangle, or I suppose I should say an exterior angle, has measure equal to the sum of the measures of its remote interior angles. So in Euclidean geometry, if we've got some triangle and we look at an exterior angle of it, this blue one, and we look at its two remote interior ones, then the theorem is saying that the angle, the measure of the blue angle is equal to the sum of the measures of the red one and the green one. And the proof of this is far easier in the Euclidean case than it was back when we were looking at the general case. Although we actually used the exterior angle theorem in order to prove Theorem 76, which we're basing it on. It's really difficult to track exactly where the assumptions could have been simplified if we were working in the Euclidean case to begin with, but we don't need that. But the point is that a point really is comparing everything to the yellow angle gamma here. So what we know from the previous theorem is that alpha plus beta plus gamma is 180. Here I'm using the Greek letters for the measures of the angles. But we also know that gamma plus sigma is 180, because they form a linear pair. And so combining these two together shows that sigma is equal to alpha plus beta. Of course, a full proof of this requires some more details. You need to walk through it and explain the reasoning more than this, but this is the idea of it. One way of intuiting what's happening with Euclidean geometry, at least in my mind, is that Euclidean geometry sort of rigidifies everything. In general geometry, you've sort of got wiggle room places. The interior angles of a triangle can be less than 180 degrees, and it's not always the same even. We'll see that when we get to it. Euclidean geometry sort of locks everything down. It says you don't have any degrees of freedom. You can't be a little bit less here or a little bit less there. Everything locks in. Everything is rigid. Now, this is a very intuitive way of thinking about it. It's not an argument, but that is a way of understanding the Euclidean geometry compared to the general geometry that we look at. Theorem 79 says that the relation of being parallel is almost transitive. It says if L, L prime, and L double prime are three lines, L is parallel to L prime, and L prime is parallel to L double prime, then L is parallel to L double prime. Now, the proof of this goes in a pretty standard way when you are trying to prove that two lines are parallel. Much of the time, the way to prove that two lines are parallel is by contradiction. Assume that they're not. Assume that there's something that lies in both of them. And this is a rare example of a place where, to prove this result, we're just going to go right back to the parallel postulate, not Theorem 76. So for the proof, we can suppose that P lies in L intersect L double prime. We're proving by contradiction, and so we assume that they're not parallel. Let's assume that there is something in their intersection. By axiom P1, there is only one line containing P and parallel to L double prime. This is a contradiction. So we have, no, I'm sorry, not L double prime. L prime is what I wanted here. So we have that L is parallel to L prime and L double prime is parallel to L prime. And if I take any point that's not contained in L prime, there needs to be only one line through it that's parallel to L prime. So in this case, we have that there are two lines through P and parallel to L prime, which is a contradiction. So that's something we can use often when looking at parallel lines, when we have multiples involved. Okay, couple of definitions. Now, this definition defining the types of quadrilaterals that we work with often, nothing's going to be surprising here. So definition 80 says let quadrilateral ABCD be a quadrilateral. So if all angles of the quadrilateral are right angles, then quadrilateral ABCD is a rectangle. If at least two sides are parallel, quadrilateral ABCD is a trapezoid. If both pairs of opposite sides are parallel, then quadrilateral ABCD is a parallelogram. If quadrilateral ABCD is a parallelogram and two sides, two adjacent sides, are congruent, then quadrilateral ABCD is a rhombus. And finally, if quadrilateral ABCD is a rhombus and a square, then quadrilateral, I'm sorry, not a rhombus and a square, I'm getting ahead of myself, a rhombus and a rectangle. Then quadrilateral ABCD is a square. So these are all completely standard definitions. And one of the very nice things that we have about quadrilaterals in Euclidean geometry is Theorem 81, which says that every secondary quadrilateral is a rectangle. And there are a number of ways that you can prove this. Perhaps the simplest one would be to take your quadrilateral, secondary quadrilateral, and look at a diagonal of it, or maybe a couple of diagonals of it, and use the fact that we know in Euclidean geometry that the interior angles of a bunch of the triangles are add up to 180 degrees, which can give you the congruences that you need here. But I'm going to leave that to you guys. We can say more here. In addition to rectangles, parallelograms wind up being very important in our geometry, and there's lots we can do with this. So Theorem 82 says let quadrilateral ABCD be a parallelogram. Part 1 says that either diagonal of quadrilateral ABCD splits it into two congruent triangles. Part 2, each pair of opposite sides of the quadrilateral ABCD are congruent. And part 3, the diagonals of quadrilateral ABCD bisect each other. All right, so this is another one that I'm going to leave you for homework, but I'll mention how we can get started. So if you can get part 1, the other parts are pretty straightforward. So let's suppose that we have a parallelogram, and we want to show that if we take a diagonal of the parallelogram, then the two triangles that are constructed here are congruent to one another. We can see that we've got one side shared between them. The side AC is shared between the triangles. We want to start there. After that, you want to start using Theorem 76. Theorem 76 is going to give you a whole lot of congruences between various angles that we see here. So for instance, notice that the line AC is a transversal to the lines AD and BC. Furthermore, the lines AD and BC are parallel because that was in the definition of parallelogram. Therefore, the two angles here and here, which are alternate interior angles, are congruent to one another. So now you already have a side between the two triangles that are congruent, a pair of angles that are congruent. You just need to find one more piece of appropriate information in order to conclude that the two triangles are congruent, and from there parts 2 and 3 follow reasonably easily. So, with the uniqueness of parallel lines, we are able to define a way of basically moving from one line to another via a process called parallel projection. And this winds up being important to us in the theory of similarity of triangles. The idea behind this is the following. We take two lines, not necessarily parallel to one another, and then we pick some point here on L, let me do this the following way. We take two lines, a transversal, that intersects the 2 points at Q and Q prime. And this transversal I'll call T for transversal. What this is going to allow us to do is to define a function that takes us from any point on L to some point on L prime by constructing a line that is parallel to the original transversal T. And if I am given any point on L, I'll be able to construct this line parallel to the original transversal T and get a point over on L prime. So it's going to be a function that goes from points on L to points on L prime, basically by moving in the same direction as a given transversal. So the transversal T we start with, and then we use it to define the movement from L to L prime. So the thing that we do need to check is whether these blue lines actually do intersect L prime. So let's give this point, this line, this blue line through P, the name TP. So we claim that the line TP, which is the line through L and parallel to T, intersects L prime. Let's see if it does. Suppose not, i.e. that TP is parallel to L prime. If this is the case, then since T is parallel to TP, by theorem, what was it? It was theorem 79. By theorem 79, since TP is parallel to L prime and TP is also parallel to T, by theorem 79, this would tell us that T is parallel to L prime, a contradiction, because we know they intersect. So that means that we know that the line TP intersects the line L prime somewhere. On the other hand, if TP is equal to the line L prime, then again, that we would have that T is parallel to TP, which equals L prime, a contradiction. So what we've shown is that the line TP is not parallel to L prime, but it's also not equal to L prime, therefore it intersects in one point because everything lies on the same plane. So this tells us that TP intersect L prime is a single point, P prime. Okay, so let's define a function. With the function f that goes from L to L prime, which takes P to the point P prime, which belongs to the transversal through P and parallel to T, and is in L prime, is called the parallel projection of L onto L prime in the direction of T. Oh, and I guess this is definition 83 in the book, or in the notes. So we've got this function that takes points on L to points on L prime. We've got a few things that we want to show about this. We want to show that the points on L prime have similar relationships to each other as the points on L under this projection. That things aren't twisted around too much. Things basically stay in the same relationship with each other after doing the parallel projection. So we have a theorem that incorporates all of that. So theorem 84, let's let f from L to L prime be a parallel projection. We have four statements here. First, f is a bijection. Part two, f preserves betweenness, and I'll just say I'll just say that. I'll specify what that means when we go to prove it. F preserves betweenness. Part 3, F preserves congruence. Basically, if there's if two segments that are subsets of L are congruent to each other, then their images are congruent to each other under this projection. And part 4, F preserves ratios. And this one I will specify. If A, B, C, and D belong to L, then the ratio AB over CD is equal to the ratio A prime B prime over C prime D prime. Here I'm using the convention that the function the function f takes every point P to the point P prime. So prime will always indicate the image of a point under this function f. All right, let's look at the proofs of this. So part 1. So we'll prove that f is a bijection by exhibiting an inverse projection. The projection G from L prime to L in the direction of the same transversal, where T is the transversal defining F, is the inverse of F. So if we've got L and L prime, and I take the transversal T here, then if I go from any point P to a P prime here using F, so F goes this way, I can also build the parallel projection from L prime to L using the same transversal T. And because these parallel lines are unique, the function G is well defined and uses the same line. Basically, the transversals, the blue transversals defined when you project from L to L prime, are exactly the same as the ones that you define projecting from L prime to L. The projection G is the set theoretic inverse of F, which means that F is a bijection, because only bijections have inverses. So for part 2, let's suppose that A, B, and C belong to L, and let's suppose that B lies between A and C. So let's look at the picture here. We've got A, we've got B, we've got C, and we have the parallel projections of these points over onto the line L prime. Over to the points A prime, B prime, C prime. We want to show that A prime, or that B prime is between A prime and C prime. So here we can use plane separation, actually. So A and B, or A and C, are on opposite sides of the line BB prime, because B lies between A and C. Since A prime is parallel to BB prime, A and A prime are on the same side of BB prime, line BB prime, and similarly, C and C prime are on the same side of the line BB prime. So that means that since A and A prime are on the same side of BB prime, C and C prime are on the same side of the line BB prime, and A and C are on opposite sides, this tells us that A prime and C prime are on opposite sides of the line BB prime. So, since A prime, B prime, and C prime are all collinear, this means that B prime has to lie between A prime and C prime. So, the function f preserves betweenness of the two of points going from L to L prime. All right, so for part 3, we're actually going to use part 4 to prove part 3. So let's prove part 4 first, and then we'll come back. So for part 4, we want to show that f preserves betweenness. I'm sorry, f preserves, oh, pardon me. Sorry, I misread my notes. We're going to need to, we need to do part 3 first. We need part 3 for part 4. I had that backwards. So we want to show that if A, B, C, D are in L, and the segment AB is congruent to the segment CD, then the segment A prime B prime is congruent to the segment C prime D prime. Rather than go through the proof in all of its technicality, which is significant, let's sketch out where the most complex form of the argument comes up and talk about how we solve it. So let's set up our problem looking something like this. Let's suppose that we have L, L prime, we've got A, we've got B, C, and D. And our assumption is that A, B, C, and D are the segment AB is congruent to the segment CD. Now we have parallel projection going up. In this case, I've written it going up because that just makes the argument a little easier to follow, to the points A prime, B prime, C prime, and D prime. Now, at this point, we want to introduce actually a few more points. What we're going to do is we're going to introduce some lines here. A line that's parallel to the line L that passes through A prime, and the line that is parallel to L going through C prime. We're again allowed to do this because now parallel lines are unique. So we've got the line through A prime and parallel to L. And similarly over here, this is the line through C prime and parallel to L. So now we have that quadrilateral A prime. We need this point over here. I'll call this B double prime, and we'll call this D double prime. We have that the quadrilateral A prime, B double prime B is a parallelogram. We don't know that any of these angles are right angles. I've just drawn them that way sort of for convenience. But we do know that AA prime B double prime B is a parallelogram. So that means that the segment A prime B double prime is congruent to the line C, to the segment AB. All right, so we have that these two segments are congruent, and similarly over here we have that the segment C prime D double prime is congruent to the segment CD, which is also congruent to the segment AB, congruent to the segment A prime B double prime. So we have that. Let's see what else. We also have that. Oh, this is supposed to be L prime over here. We also have that L prime is a transversal to the transversals TB and TD. And because and TB is parallel to TD, so we have that corresponding angles are congruent. So we have that the angle here and here are congruent to each other. And similarly, we have that the green, or we also have that L prime is a transversal to the green lines. So we also get that these blue angles are congruent because the two green lines are parallel to each other. And therefore, we have that the triangles A prime, B double prime is congruent to the triangle C prime, D double prime by angle, side. So that works. That gives us the congruence between the triangles. So in particular, this tells us that A prime, B prime is congruent to C prime, D prime. So that's the idea behind showing that the parallel projection preserves congruences. Now there are lots of cases that we didn't consider. What if B and C are the same, etc. But this is the essence of the most difficult part of the proof. All right. So finally, we have that parallel projection preserves ratios of segment lengths. So part 4, F preserves ratios. That is to say that AB over CD is the same as A prime B prime over C prime D prime. All right, so for this, let's go ahead and A, B, C, and D. I don't know why I'm putting tick marks. Those should just be points. And we've got a parallel projection over onto the line L prime, which is now on the right side. L prime. So what we're going to do here is we're going to show that these two numbers, which could be irrational, there's no reason that distances have to be integers or rational or anything like this, but what we're going to do is we're going to show that that the set of rational numbers that are less than the left-hand number in this equality is the same as the set of rational numbers which are less than the right-hand number in this equality. And that's going to be, that's actually going to be good enough. So let's let P and Q be positive, positive integers such that P over Q is less than AB over CD. So now let's let A0 be the point A0 be the point A, and we want to choose points A1, A2 up through AP such that each AI lies between A and B, and each AI minus 1 AI, the distance between any two of these A's, is equal to CD over Q. So this means that the distance from A to AP is going to be equal to P times CD over Q, which is P over Q times CD, which is less than AB. So what we're doing here is we're choosing a bunch of points here. A is going to be called A0, then we got A1, A2, all the way down to AP. And the point is that because we've chosen for us to have P of these little segments over here between A and B, and we've chosen for each of the segments to have a length equal to CD over Q, their total length is P over Q times CD, which, based on our hypothesis about P over Q, is less than AB. So in particular, this means that we have the between this relationship A to AP to B. And therefore, we also have that when we project everything over to L prime, and we'll get A0 prime, which is A prime, A1 prime, A2 prime, all the way down to AP prime, that means that we'll get that P times A0 prime A1 prime is we'll get that A prime AP prime is less than A prime B prime. And now we sort of just unwind it the other way. We know that the distance from A prime to AP prime is going to be equal to P times the distance from from say A0 to A1, A0 prime to A1 prime. But we also know that because each one of these distances from an AI to an AI plus 1 is equal to CD over Q, each of the distances from AI prime to AI plus 1 prime is going to be equal to the distance C prime D prime over Q, because F preserves congruences. Basically, what we could do is we could set up, we could split the segment CD here up into Q segments, and then each one of these segments would be congruent to each of the little segments up above, which means that when we project it over onto the right, we will still have Q segments, and each of these segments will be congruent to the primed segments that we got up with the between the A prime and the B prime. So, in other words, we have that A prime AP prime is equal to P times A0 prime A1 prime, and A0 prime A1 prime is equal to C prime D prime over Q. Thus, we have that P over Q times C prime D prime is less than A prime B prime. So that means P over Q is less than A prime B prime over C prime D prime. Now, this is true now for all rational numbers less than AB over CD. If the primed ratio were less than the unprimed ratio, if A prime B prime over C prime D prime were less than AB over CD, there'd be some rational number between them. There'd be some rational number that's bigger than the primed ratio and smaller than the unprimed ratio. This argument that we have here says that can't happen. If some rational number is less than the unprimed ratio, then it has to be less than the primed ratio. And that means that A prime B prime over C prime D prime has to be greater than or equal to AB over CD. Because if it were less, then there'd be some rational number in between them, and we've just shown that can't happen. So that shows one direction of the equality that we want, but to get the other way, we just project back over. We use the projection from L prime to L in the same direction, the inverse projection. The inverse projection shows that AB over CD has to be greater than or equal to A prime B prime over C prime D prime. And so that finishes it off. The fact that parallel projection preserves ratios is going to be absolutely essential to our next topic, which is going to be discussing similarity of triangles. We're going to leave things off for here now, and we'll see a lot of those applications in the next video.